So I've been working on a few things with GunClear. Um, I have two things called plasma. I'm going to show you plasma rifle first. I have a few things demoable. Just pull up the instructions in case I forget something. So I had a few just utility things that'll demo me, create a demo key for me. So that's the fake private key I'm using for this exercise, and it generates this Ethereum account, similar to how it will work in the app. And yeah, I'm gonna get rid of that. And get rid of that. Cool. So I'm gonna deploy my gun. I'll do the auth list first. So this is the on-chain authorization list that we have for GunClear. And we're going to deploy it to the Ropsten network, test network. And this one has no arguments, I believe. So I'm going to unlock my wallet. Say yes, I want to deploy a new auth list. It's an Etherscan link. Gonna share that with you guys. So,
and just what are we seeing here, Bryant?
This is Etherscan, so it's a public tracker for the public testnets, and it lets us see transactions in motion on the public testnets in the same way that you would see it with the mainnet.
Okay.
So you got to wait a bit for that to log. Should only take about a minute or so.
So I guess while we're waiting here, do you want to kind of go into what exactly is? Oh, and there it goes.
Yeah. So behind the scenes, we have our compiled contract, and it's getting deployed to a new address on the Ethereum network, this specific test network.
Okay, and what does that allow us to do?
That allows us to execute the contract. So created this new contract here. It's from my account. And we need that for later, so I'm going to switch back to my terminal. I'm just going to save that for later. I'm going to do the same thing for my token.
So you're deploying a token.
Yeah. Because everyone likes tokens.
What does this token allow us to do in relation to the GunClear system?
So the tokens are kind of standing in for the physical asset that is the firearm. And so there's a process by which a authorized GunClear member can provide documentation for a firearm without revealing their identity to GunClear, and GunClear will review that documentation and decide to issue a token for it. And once that token is issued, that firearm owner is freely able to transact with other GunClear members using that token as a digital representation of the ownership of that firearm.
Excellent.
How's that guy doing? Oh, success. That was much faster. Cool. So let's just do something fun first, and we'll mint ourselves a token. I'm just going to go grab a random account from Etherscan. So for the purposes of this demo.
That's fine.
Cool. So here's a transaction that just popped up. And I'm going to give this person unwittingly a GunClear token. They're not even going to know. But they're going to have one.
They are.
They're going to be lucky. They're going to have a GunClear token. Okay, so I'm going to do... Need to give it the address of the token, so I know which contract to call. And also going to give it our random new person's address. What token ID do you want to use, Steven? Just give me a random number.
45212.
45212. Okay. We'll add a 7 in there just for the heck of it. Cool. So do I want to emit that token to this random address? Yes, I do. So we're waiting for that. I'll share that screen because that's kind of fun. So in the GunClear system, once we've reviewed the documentation, decided we want to do that, we will mint this token to this person. It's an ERC 721 compatible token. So any on-chain services they decide to use or want to use with it, they can try to use it, but it doesn't quite matter for the GunClear application because it spends most of its lifetime locked in the plasma bridge to the Gonero network. But the fact that it's issued on Ethereum allows the user to have more confidence that that token is handled with higher security. And if there was ever to be a problem with the GunClear application, they could withdraw their token from that bridge and use a different service that offers similar functionality. And this means that you're not locked into the GunClear ecosystem. The incentives are such that we're aligned in offering the best utility that we can for our users, and if we don't, then they're allowed to exit the system.
Okay. You mentioned the Gonero network. Can you just speak a little bit about that? What is that?
So that's our cute little name for our Plasma sidechain. So Plasma is a scaling paradigm that Ethereum has pioneered that allows sidechains issued against the Ethereum main chain to have an exit mechanism that allows users from the sidechain to withdraw their tokens from the sidechain at any time without relying on the operators of that network respecting their queries. So you would take this token here that was issued on main chain Ethereum, you would lock it into the Plasma side bridge, which I can show you a little bit of a demo on how that would work. And then after that, we would by doing that, you would have access to the GunClear network, which is this zero knowledge trading network that we're building. But if at any time you decide you want to exit that system and withdraw or burn your token, you're allowed to do so. We have to respect that because that's how the plasma paradigm works, is that the operator is not assumed to be always operating effectively. They are assumed to be occasionally malicious or whatnot. So the plasma paradigm designs for a malicious operator and ensures that there's recourse in case there's some issues with the network and the user decides that they don't like that.
Awesome. I'm just
So
is this a successful transaction here?
So we successfully issued ERC 721 token here. Really cool thing is that because we're using that standard, you can see here in the transaction, it just automatically recognized that that's what we're doing, and that's what we issued. And it shows that we minted that token.
Awesome. And it actually looks like it didn't cost any money in the actual costs.
Yeah, don't pay as much attention to that. It's
I was looking lower at
it's a test network.
From a gas standpoint, though.
From the gas standpoint, we paid that much. So our real transaction cost was that. Main net is about 10 times that. So times 10 times what? It's 150 bucks right now. Be about 13 cents. But that's an important thing to bring up because GunClear would actually be issuing the token, so GunClear will be paying for these gas costs.
Right.
So we pay these higher transaction costs for our users in order to give them that security that their digital asset is being handled correctly.
And in terms of the cost that this transaction, how much was that?
It was 13 cents.
13 cents. Okay.
So it's priced into the costs that we charge our users, and it's much higher cost than using something like AWS, but that's because the security and mental models are completely different. We want to make sure our users have that high degree of censorship resistance against us ourselves being censors of their activities. So because we're issuing it on Ethereum using this plasma paradigm, we never have full control over this asset. The user always retains control once they're issued the token.
Cool.
Cool. So I'll switch back to my terminal here. And now we're going to work with the authorization list. So that's cool that this we gave this person a token. Cool and all, but the problem is that they can't transact with it in our GunClear network because they're not an authorized user. And usually this would actually occur. You would be authorized as a user before we issue you a token because this authorization mechanism allows you to generate the zero knowledge proof of membership that you could use to completely anonymize your identity when you're asking to have a token minted on our network. So I'll show you a little bit about how that works. So we have our first thing we have to do though is we have to get synchronized with the network. So every time, so on deployment, we start with a specific value for the root chain hash, which is an important public parameter used for the zero knowledge proof. And we have to resynchronize our branch to that root every time that we interact with the network. But thankfully, we've issued against that. Thankfully, every time an authorization is handled or any sort of status change of an account, the updated Merkle nodes are emitted in events, so you can just cycle through the events and get all of the updates and process them sequentially. So we'll do that. So we have our account here, and this is our random person. And it creates a huge list of all the, not that big, but it's 160 32-bit hashes. So that's 160 times 32. That's about 5 kilobits of data that we need to keep track locally on the user's machine. The good thing about this algorithm is that it's statically sized in terms of storage. So that 5 kilobits is all that's required to keep track of this proof. There's a couple other bigger ticket items in terms of local storage, but it's all statically bound, so there isn't a growing storage cost for the user. So we're going to save that to a file, so I don't have to carry that around everywhere. And we'll save that to a file too, just because. Cool. So now I can authorize this user as the GunClear authority. Once they've given me the necessary identity documentation that we need. And as I said, this would be done before the token would be issued. So once they give us that necessary identity documentation and we decide we like it, we would go ahead and authorize that user. And that's a pretty easy process. Let me just type all this stuff out. And now we're going to authorize that user. Yes, I do want to authorize them. So we're going to go back to our Etherscan, hit it in a Etherscan. Wait for that to work. So when this user's authorized, that list of 160 hashes that they're keeping track of stays constant, but the node updates that authorization change has caused will be communicated to all the other members of the network through the Ethereum event system, so that any actively listening light clients of the Ethereum network, including our users, can go and grab this information. And the nice thing about that is that since we do that kind of in a broadcast fashion using on-chain events, that there is no risk of censorship from us disallowing somebody from us doing it on chain and issuing it through on-chain events. Anyone of our users can listen to these events from the public main chain Ethereum and grab what they need, and they will not be censored from getting those updates because it's provided through a censorship-resistant system, and that means they will always be able to generate this proof in order to do their private transactions in a zero-knowledge way. So it doesn't show you much, but the event logs, these are the list of all the node updates that the clients will listen to. The status update, we change from a 0 to a 1, and this is our user here. And the algorithm just uses the user's key and finds the first point of branch between the 2 points. And the algorithm will find the location in the list that that branch point occurs and update that hash to what they have. So it's a pretty constant time algorithm. Just you have to iterate through all of the different authorization updates, but that's only hopefully 1 per account. So it should be a fairly low volume of authorization changes, at least for a pretty long while. And that will update the state root which is that public parameter in the zero knowledge proof that ties all of the authorization statuses of all of our users together in one public parameter. So that's how you're not revealing anything about your identity when you're approving membership in the GunClear system. Does that make sense?
Yeah.
Cool. All right. What else do I got for you? I think there's one more thing. Oh yeah, just to show. So this is just a little utility to help get that root that I was talking about.
What is you showing right now?
So this is the root hash. So this number right here is extremely important to all the users of the network. So every 7 days, this number is resynchronized with the plasma chain network. And this number is used as a public parameter in the zero knowledge proof of membership in the GunClear system. So this hash will be used to authorize two users to perform a transaction between each other, so that we know that they're authorized GunClear users. We know they're in that system. We just don't know who they are exactly because they're not showing their identity. They're only showing the fact that they're in the GunClear system. So it's kind of like having a membership card where it has no personally identifiable information on the front or back. It's just something we can trust was issued correctly, and we, maintain the list of people who have or have not that membership card. But with that membership card, they're allowed to completely privately and anonymously transact their digital tokens that represent the firearms without any fear of surveillance.
Awesome.
Cool. So the last thing I want to show is that we can get the updated roots for any account in the system. So how does this work? So we have our user here. And if you notice, this doesn't actually update for this user. Oh, it does update.
So what just happened here?
I think I did something wrong. That's what happened. Yeah, I did something wrong here.
No worries, we can cut it.
Cool. So there's no difference between. No, you don't have to cut it. There's no difference between what. So when the user itself gets an updated authorization, they don't have to update their proof, but any other user, just change that number there, would have a different proof update that they would have to handle. But it's only one change per user. So this is how that system that was designed works in order to make sure that in a censorship resistant way, they can keep track of all the proof data they need to show their membership without fear of us not giving them the updates and somehow censoring certain accounts. We can't do that. The only way we can, there is no way that we can censor anyone from being able to provide this proof. As long as they're on the list, they're on the list. So I believe that is all I have for you today.
All right, while Brian was running the same demo, I was also running a separate application in the background. This is the ZK Snarks version of the same application. In order for these to work together, there's these separate components. The primary, the plasma, the GunClear operations, those are all networking components that work with either the Ethereum system or through the application communicating back and forth between our separate plasma blockchain. What has to happen on each individual user's phone or other computer is that they need to run this application type called a ZK snark. What will happen is, this is the latest technology, and it's also the most time-consuming and a difficult one to work with. Rapidly, what we're working on right now is defining the standard itself. So what this does is it allows the user to prove that they have access to any particular token or object, in our case, the non-fungible token that represents the transmittable token for a gun that they can sell, and prove their ownership of that token and their ability to transact with another user who they'll be transmitting the token to in a way that they can publish a proof of that information to the wide world, including us as the maintainers of the system, without us actually knowing what information it is, not knowing the details about who it is who's transacting and the specifics about the transaction itself. This ZK snarks, as you can see in this window here, it's the way that we have this, the way that users prove their existence is to do using the same files that Bryant has just run, the accounts and the uncle information. You can see here the Ethereum account information and corresponding 160 hash values that correspond to these that you saw also in the Robson test network. What we could do here operation, and by its nature, it will actually go and calculate, proving definitively as it goes along that there's no hacking, there's no alteration, there's no faking of ownership. All of this information is exactly true based on what the user has. We can see here that this is the generation, what in Zcash calls a toxic waste. What we can do is from our side, from GunClear's side, we can actually generate these ZK snarks and have this as a circuit, a little running program that the users will have in memory and run whenever they need to. And this is a toxic waste. We have the ability to waste process. We don't have to go through a setup ceremony that Zcash had, because as a part of the setup had access to the toxic waste, whereas we, from our perspective, can guarantee that's not an issue. There's no way to generate a false transaction because all transactions can only be through a non-fungible token. The token has to exist. You can only transact from one location to another. What will now happen in this case is we simply need to show that the user is correctly running this. So the user will have this circuit that they run. Now, because of the large number of variables, these 160 uncles, the other information that's included, as you saw in the Robson test network, this has a very large demand for the amount of memory and variables being held here. Zcash and some other ZK snark systems have a very large number, maybe millions of these variables of memory, but this is what we have here is a very, very large number, about 50 million elements, making this basically largest ZK snark in existence right now. We need that memory and these components to be able to prove that definitively nobody's, the user is not faking it. So this makes this extremely secure. So if any particular element were to be faked or hacked, that's a very low, it makes it nearly impossible.
So one thing to note, thing to note is that that proof only has to be generated once a week, and that's a conscious design decision on our part because it does take a little bit to actually run. Currently, I think it's about 40 minutes on my machine, but will be a lot less in practice once we're done optimizing it. It still may take a few minutes to run, so in order to have a good UX experience for the user, we chose that time of 7 days. So that means that within a 7-day period, you're able to transact using that same authorization proof. And on that 7-day cycle, it'll change. You'll have to regenerate the authorization proof. That also means the onboarding and offboarding of the system occurs in 7-day cycles. And if there is a dispute in the authorization status of a user, we actually have a dispute mechanism in place, or it'll take almost a month in order to revoke their status. Within the week, they'll become on a different status from other users, so it'll actually reduce the anonymity set of users that may have suspicious activity and been nominated by other users as being like that. So that's how we manage the onboarding, offboarding of the system. There's actually a process in place for how the authorizations change. And in order to promote good UX, we have that proof only generated on a 1 week. Sorry, Sean.
And as Brian mentioned, this can be run. This needs to be run once a week to prove that the user has correct authority to exist inside the network and to be able to transact. The nice thing is this is not user interactive. This is simply run in the background on whatever computer the user has, and it will run in basically needing only modest amount of processing power. It might just take a while because of the memory use, and we're preparing for more thorough optimized build so that it would take up less memory in total. But right now you can see there's a modest amount of processing power, just simply one single thread, and a good amount of memory being used. Right now it's proving membership for a particular user, the same demo user that Brian had done before. So that's going on in the background. And you can see this amount of memory being used is modest for a desktop, but challenging for a mobile phone. The newer versions that are going to be developed will have a lot more optimization, go a lot faster, take a lot less memory.
Awesome. And then a question about the weekly update. Is that automated by the system, or does that have to be manually done by a person?
So that's how we designed the Plasma system. So that 7-day sync cycle is actually the synchronization period of all the transactions that occurred on the subnetwork. We're currently aiming for like a 2-minute block time. So that means when you do a transaction on the network, you should receive a response about whether that transaction was accepted within 2 minutes. And then all of those transactions over a 7-day period are collated together and uploaded through a single 32-byte hash to the Ethereum network. That gives the scalability of the system, because you're making all transactions that occur on our network summarized by a single 32-byte hash that has certain properties that are makes it able to have that security. But so we do that on the weekly basis too, and that updates the authorization route that we use in order to make the transactions on the network. So every 7 days, those two are kind of swapped and updated. So that's probably going to take a while to run. Do you think it would be possible to run some of the other proofs on a separate window? Or do you need that to work?
Sure.
Hopefully your computer doesn't.
No, the nice thing about the ZK snarks is they're all single-threaded.
Yeah.
Yes, there's not going to be an issue with the other ones. We have two other, let me see, proofs that we can, just give me a moment.
So in a transaction, both the sender and receiver of the token would have this authorization proof already generated on the side, and they would have the proof data available to verify, and verification takes very little time. You were saying like 200 milliseconds, Sean?
Oh, the verification is, 200 milliseconds is actually very pessimistic. Normally we get it under 30 milliseconds total from the verification side.
For the
ZK snarks are designed to be,
okay.
The other items, it's even going to be faster than that. It's just not a single or just slightly double-digit milliseconds. So mass volumes would be no issue at all for our servers.
Yeah. So within a transaction, you'll have the sender provide their authorization to the receiver, who would verify that, yes, they are indeed a GunClear user that is authorized to do transactions. And they would also give some of the private data concerning the token, so they can verify that the token is correctly aligned with the asset. So you can kind of think of it as a second factor authentication, like a digital attestation to that asset. So you can be sure that, if it's, you have it in your hand, everything looks good in your hand, and you have this digital kind of certificate, if you will, for the firearm, you can kind of be really confident that that asset is indeed working the way it should, which is nice. And then, so the receiver will take that information, they'll produce a spendability proof, or a receivership proof, sorry, and that will give an approval to the system that they are accepting this token. And they would give their authorization, their approval to the sender, who would compute one final sending proof or spending proof that authorizes changing the token's ownership from their ownership to the receiver's ownership. And then once all those proofs are kind of computed, you would upload it to the network and broadcast only the public parameters, which is basically just the token ID and the authorization proofs that don't reveal identity, only reveal the that the proof was adequately handled, and they're all tied together in a certain way that we've designed to make sure that all the proofs are consistent with each other. And then the network will take that, verify that, and be able to move a transaction from one person to the other, move a token from one person to the other. So as Sean was saying, it's about, I guess, 30 milliseconds. It's the worst case for the proof. So the total executing a transaction should take less than 200 milliseconds.
Oh, yes. Yeah. The total end-to-end will be about that, less than 200.
So at 200 milliseconds, that's obviously about 5 transactions per second. I think that's pretty much our biggest bottleneck in the system. And with total gun ownership and gun transaction estimates, we should be much less below that cap for the amount of transactions we can handle.
Just a qualification on that one. It's actually it would be 5 transactions per second per core of the server. And so in the case of a multi-core server, we can scale.
Yeah, and that's before accounting for the fact that we can parallelize a lot of these operations.
Yes.
So it sounds like this is actually scalable right now.
Yeah. I think even at the top, like there's 400 guns in the U.S., and if every single one of those was traded within a year, it would still be less than 5 transactions per second. So, we've done a lot of analysis, at least very loosely, about what the limits are of the system, and this is a good system to pick because it's actually fairly low but fairly high. It's high security and high importance application for the technology.
And right now, I'm going to run a proof for both the other 2 components of the proof that we need to run. These can also be run in parallel, like they would be should we actually have a transaction going on. We can see here, generally what will happen is as 2 parties interact with each other independently on their computer, so these will be going on. This demonstration should show it will just take a few moments for the transactions to occur. And these also have much lower memory usage than the main membership proof, which requires a significant amount of processing power.
Yeah, so this would be generated on the user's device as they're in between the transaction. They're checking over the firearm. We'll make sure that there's good UX feedback to the users so that they know this is happening without knowing all the technical bolts and nuts, and they're given an opportunity to kind of discuss with each other, check other things about the firearm, physical attributes of the firearm, and all that kind of stuff. So we'll have a mechanism that an owner can prove that they own the firearm without having to release it. So this would be an opportunity to check over that the serial numbers match what was originally tokenized for, and that kind of stuff. So Takes what, 42 seconds on your, or 76 seconds on your device to do the spending
Yeah,
proof.
yep. The approver ran verification had a glitch, but this is 76 milliseconds for, or excuse me, 76 seconds total for the proof on one side.
And on the other side, it looks like it's going to take a little bit longer than that, but similar amounts of time.
Right.
And so this is in an unoptimized state. We're hoping in an optimal state that it will hopefully take less than about 2 to 5 minutes to actually conduct the transaction. Hopefully under 2 would be ideal. That means there won't be too much awkwardness in the actual physically present transaction of using our system in order to verify the ownership, do that kind of second factor authentication that the firearm is legitimately owned. Did you kill that? Yeah. You killed it and restarted it, so it might take a little extra time.
Yeah, yes,
Can you, with the other one, show the proof? I mean, show the verification of the proof? So you generated that spend proof.
yes. Perfect.
We just want to show how fast the verifications of these proofs are.
Now, this is a verification process for just membership. Now, the membership takes the longest amount of time to
prove.
run. But as we can see here, this is yes, to generate the original proof to show that the user is actually authorized for a particular 7-day period. It takes the most amount of time in memory to do so. But from the verification process, when we have either other users verifying that the other person is a verified member, they'll simply load up their verification proof and guarantee that they can interact with the person. Alternatively, sending that up to our the blockchain, the GunClear system, and then from our service perspective, being able to verify that the proof, that we have them go through this verification process. Now, if they haven't proved, it takes mere milliseconds to run. Now, this is an unoptimized system right now, and I just ran this. And it just took for the entire process of loading the files, running it, and then completing 43.4 milliseconds. This is unoptimized in debug mode. So if this is running in release mode, the verification is much faster. So yeah, it's significantly less than this. 43.4 milliseconds is actually, I think, probably the longest time. Just,
wow.
And also the other.
Oh, it looks like the other one finished.
So, yeah, 2 minutes for.
2 minutes?
Yes, it's running in debug mode.
Oh.
2 minutes and 20 seconds, but that's also in debug mode. The release mode is much faster than that. But yeah, so verification for the membership, which is our slowest verification. At worst case, now there's other verifications we can have as well. So let me verify the send and receive. These would only be shown on the GunClear interface, whereas the users could verify each other's membership as a prerequisite for beginning a sale. So in our case, we won't see these results, but in the case of verifying some of the sends, for example, the send proof is about 26.6 milliseconds unoptimized. And rather the proof and verification of the receive, in this case, got 41.3 milliseconds. That's also an faster process with better memory. Should go quicker.
So as I was saying, the throughput of the actual network is related to all these verification times, and as you can see, they're all pretty short. So we can handle that 5 transactions per second with no problem, which is great. So in terms of what we have so far, and what kind of next steps are, obviously optimization is a big part of what we have to do, especially for the zero knowledge proofs. We have to go through and show that and be able to get good performance on a mobile device. That's going to be a challenge, but hopefully we're able to use some UX tricks and some other things to get that down to a reasonable time frame, aiming for about that 2-minute interaction period, and so that the users don't feel too awkward doing this interaction. And once we're complete with that, so that's on the zero knowledge proof side. We're also looking at optimizations on the size of the membership proof, the one that's generated every week. We have some plans for optimization to reduce the amount of hashes that has to be done from about 160 to maybe somewhere on the order of 30 or 40, which should be a not a quarter reduction, but an exponential reduction in the amount of memory and stuff that's used. Correct, Sean? Is that correct?
Yes, that's right. Yeah, it'd actually be even faster than that. The operations are much more simplified. The amount of variables we need are much more constrained.
Yeah, so that's just one kind of naive optimization we can make, is lowering the size of the tree. We're using the full 160 bits that an Ethereum address takes up, which is an astronomically sized grouping of addresses, whereas we think about 30 or 40 bits will be appropriate to track all the address space that we need for our users in our ecosystem. One last thing I wanted to show. Did you have anything else you wanted to show, Sean?
No, I'm good.
Yeah, one last thing I forgot. To show off is my plasma thing. So I'll do that.
So what's your plasma thing? What are we seeing?
Yeah, so I was in order to prototype our how our plasma system would work using these zero knowledge proofs and some other alternatives that we have in our system versus like normal like token based financial kind of applications for plasma. So we have a couple different paradigms there, but so I worked on prototyping just a from actually Georgios's white paper, a version of Plasma Cache, all written using Viper contracts and using Python instead of some of the JavaScripty stuff. So I have some of that stuff here. So the contracts themselves, I written root chain implementation for Plasma Cache and Viper. Started actually taking some of the designs and features of Plasma and proposing them as feature requests for Viper. So we have this, get Merkle root function that we're aiming to put into Viper, handling of signed transactions that'll be put into Viper as a kind of first-class citizen using EIP 712, and kind of simplifying the implementation a little bit so I can have a really good understanding of how Plasma Cache works. So later on, we can effectively design an alteration to the Plasma Cache design for our ecosystem. I wanted to do that in order to have just a good understanding of what's going on without having to worry about too much about trying to get our system designed perfectly on the get-go. I'm doing all my learning by building this prototype for general Plasma Cache. And just to show it in kind of in action, I have high-level test cases. I'll clear that. So I have high-level test cases that operate on the sort of core Plasma Cache design. These entry and exit mechanisms will be in our final application, but I'm also using this this prototype of Plasma Cache to do work on state checkpointing. So currently, a deficiency in the Plasma Cache design. There's actually two deficiencies in Plasma Cache design that are being researched. One is the size of the proof data you need to retain. So in kind of naive Plasma Cache, you'll have to retain for every single block that's ever committed to the network, you're going to need to keep track of proof data. Merkle tree proof data for that token. So that's obviously a linearly scaling amount of data that you'd have to hold on the device, and something like a couple gigabits per year or something, which is kind of totally untenable for our users. So I'm working on a checkpointing scheme that would give an absolute bound to the amount of storage space that a user would have to control, and I think it's about 12-ish blocks or 20-ish blocks of data, which will be much, much less than a couple gigabits, probably on the order of a few megabits of data that the user will have to store per firearm owned. And this will, hopefully give a nice bound to the amount of storage space that's used in the device, which is obviously at a more of a premium than the bandwidth. The second thing that needs to be worked on is the data availability problem in plasma designs. Usually that's handled with a complicated bloom filter approach. And I'm trying to prototype a alternative approach, also using kind of the checkpointing mechanism as a way to turn that conversation between malicious and not malicious users to I'm keeping track of my local data, and if I see something amiss from the operator, I will kind of enter in what last I knew it was and ask the operator to prove that there is a valid transition to a different set of data that the user isn't aware of. And if the operator successfully proves and shows that there was a valid transition, then that means the user now has updated data that they can use for the next time. And if they can't show, or they don't decide not to show a valid transition, they'll actually be kind of slashed and have their published blocks removed from the system. So there's this, I would say, about a month period of this checkpointing time that I'm aiming for. So within that month, the transactions are mostly finalized, and then after that checkpointing period, they're completely finalized. They're unable to be reverted at that point. So the client itself will just make sure to keep an eye on things and making sure that no kind of fishy things are happening with the main chain exit mechanism. And this is just kind of a state of the art of how plasmas have to work, plasma designs have to work. But there's this really good guarantee that you won't have an exponential growth in the amount of data that you'll have to hold locally. You won't have this data availability problem, at least as far as the amount of actors you'll have to consider, and that data availability problem, and the kind of recourses that you have in combating against that. And then hopefully if we're able to prove the efficacy of that design, we can use that in our scenario. If not, we can use just kind of the naive approach and work on more optimizations later. So this is kind of a second order research problem that we have. All right, so that's what I wanted to show you guys. We have a working test suite for that.
If you could just kind of give a high-level summary of some of the accomplishments or milestones you guys are most proud of, I think that would be valuable.
Sure. I think the biggest thing is working on the membership proof. We were able to provide a series of technologies, including zero knowledge proofs and on-chain handling of the data that allows that membership proof to be conducted. So that shows that you're a member of a list of people that are authorized for a particular action, and you're able to produce that proof in a zero knowledge way. We're able to maintain the proof data for that in a sort of metadata resistant fashion. So in our on-chain example with the authorization list, that is resistant against any sort of censorship, and there's no particular grabs of data. You're kind of processing all the data. So it's more difficult to make a determination of which specific actor you are in the system. You can only tell that they are not accessing that data. So you kind of get that anonymity through like a large crowd approach to metadata resistance. That's one of the biggest accomplishments we've made here. Working on the plasma cache prototype. That's kind of the first example of plasma cache written in Viper, and we're feeding back those back into the open source project in order to make it just easier and simpler to write plasma designs in Viper in that programming language. And Sean can speak to some of the accomplishments that he has made.
We've extended the snarklib application to create what's called a sparse Merkle tree, which is what we're using here. There have been no sparse Merkle trees implemented before. So that code is brand new. We've also created, because of that, the largest snark circuit of any of the published items. And we've created some unique solutions to some minor problems dealing with circuits as well, too. We also have, I think this is the first case where we've had a dual proof. In other words, a transaction has to be proved by both the sender and receiver. This is similar to some other theoretical actions, but historically everything's been a unidirectional proof and that only one party needs to prove party proof, which is similar to, say, Nimble and some other proving systems. So this is jumping ahead on some theoretical issues, and we've extended out what the capability is for the rest of the community. And we're also working on some other items that will be released in open source and provide in request for feedback from the community as well. So yes, the sparse Merkle tree is unique. So that's a big hit.
And we've also done another proving thing is that composable proof. So our proof is composed of 4 separate proofs, and the way that those proofs, the way that the public data of those proofs interact, we are able to show that each proof ties together in a specific way, and they can kind of be considered as a set. I'm not sure if that's been done before, but I think that's a novel approach.
In ASAP too, I don't believe there's any ZK snark in this plasma style chain before. This is the first time this theoretical concept has been talked about, but it's actually implemented for the first time here.
Awesome. Sounds like a lot of firsts.
Right.
Yeah, we've been very busy these past few months, and we're hoping to keep pretty busy in the coming year.